Okay, what is the Cartesian velocity? If you have a manipulator and if you spin the joints with some angular speed, the end effector will track movement in the xy plane. The xy plane is the Cartesian position, so the rate of change of that position is the Cartesian velocity. Okay, so that is basically this thing. Cartesian velocity is movement in the x, y direction. So we're only going to look at planar motion, so just x and y. So rate of change of x and y. Okay, so maybe this is more illustrative. So if you have a manipulator like this, and then you're interested in knowing how this moves, x dot, y dot, given these angles and the rate of change of these angles. So theta 1 dot is known, theta 2 dot is known. It will basically tell you how to compute x dot, y dot. Kind of useful, right? How you want to know how fast your end effector is moving. That comes from Jacobian. So let's see how to do that. It's actually a very straightforward computation. So here's some theory which will tell you how you actually get the velocities. So let's say that this point is P, okay, or let's just put E for the end effector. Okay, so let's put E0. So that's the position of E in frame 0. Let's say it's a function of f of q. This is something we did in the past. It's called the forward kinematics. So you can refer to your notes in the notes. You see a formula, or if you remember, it was the homogeneous matrix which gave us what is the position of the end effector given the joint angles q. Q is theta 1 and theta 2. It's a joint angle, so of the manipulator. Okay, so what we're going to do is we are going to use the Jacobian to do this. So J is df dq. This is just the definition. And you can take the derivative of anything with respect to anything else. F in this case is a dependent variable, and q is an independent variable, something we need to specify, and f is a result of specifying the value of q. So that's J. I'm going to move things around. Q equals df. Okay. Yeah, what I'm going to do is next, I'm going to just take the divide both sides by dt. And when I take divide by dt, I can actually replace the partial derivative with the complete derivative, because time is, there is, when you have time, when you're trying to take the time derivative, there's nothing else which is going to be floating, in the sense that when you have, when you talk of partial derivative, usually there are two directions like x and y, and when you take a partial derivative, you keep one constant, you move the other one. But time by itself is like a absolute quantity. There's nothing else which is going to be changing. So it's, you can just replace it with dq dt, and then df dt, where t is the time. Okay. So what is df dt? F is nothing but E0. So this is basically dE0 dt. It's the rate of change of the point E, is this point, with respect to time. Okay, so rate of change of that point is basically the movement of that point in the Cartesian plane. So we have J dq dt. What's q? Q is theta 1 and theta 2. So if you take the derivative of q with respect to time, it's simply theta 1 dot, theta 2 dot. And then this is dE dt. So E, the position E has coordinates xe and ye. So if you want to take the derivative with respect to time, it's basically xe dot and ye dot. So xe dot in frame E, frame 0, and y dot e in frame 0. Okay, so there you have a formula which says that velocity of point E in frame 0 is nothing but the Jacobian of uh, of that power kinematics df dq times q dot or theta dot. So that's the formula. So this is just comes from the definition of df dq. So if you want to do that, the only thing you need to compute is j. Usually, you know the velocity of the links. You need to know that. Otherwise, you cannot calculate the velocity. But you can calculate the velocity from those two things. Okay, so let's see how to apply this on a two-link pendulum. Okay, because that's the one we've studied in the past. So I'll compute the velocity of the end effector like the one I have over here. And that has actually many uses. We'll see some of the uses a bit later. One is you can actually do the inverse kinematics if you know the velocity. You could also do the dynamics, which is trying to write the equations of motion of a double pendulum if you know this velocity. So let's see the application of this formula. Sample. Yes, I'm going to draw it this way. It's slightly in a different orientation compared to last time. And let's say that this angle with respect to the vertical is theta1. And then we always, to find theta2, we extend the first link and compute the angle weight with the second link like this. That's theta2. Okay, and then what we'll do is, instead of the end effector, and what I'm going to do can be done for any point, we'll actually compute the velocity of the center of mass. Okay, and I'm going to assume that the center of mass is at a distance of c1. So let's call that g1 and g2. And then this distance is c1, and this distance is c2. And then I also would need the link length. Okay, I don't quite need the length of the other link for this case. Okay, so the question is compute the Cartesian velocity of the center of mass G1 and G2. And so what we're given, here's a given. So we are given C1, C2, L, theta1, theta2. We also given the rate of change of those angles. And we are asked to compute velocity of G1 in frame 0, unknown, and velocity of G2 in frame 0 is unknown. Okay, let's get back to the Jacobian. So here is the manipulator. We are trying to compute the velocity of point G1 and G2. What we'll do is we'll fix a frame and then go from there. So what I'm going to do is I'm going to fix a frame such that x-axis, x0 is along the horizontal. So let's just fix x0 this way, y0 on top. Okay, And then remember, what we want to do is for every link, we want to have its own frame. So let's fix the frame for the first link like this, x1, y1, and then x2, y2. Okay. So now let's write down the formulas which will help us identify what we actually need in order to do this computation. So we want to compute the velocity of g1, which we saw was simply the Jacobian of g1 times q dot, right? So jg1 q dot was theta1 dot, theta2 dot. And then we need velocity of g2 in frame 0. That's going to be jg2 q dot. So jg2 theta1 dot, theta2 dot. Okay, so what we already know is we know these things. These are just given to us, so it's already solved. The only thing which is left to compute is this Jacobian. So let's compute the Jacobian. So the Jacobian of G1 is nothing but the forward kinematics of G1. So we need to compute the position of point G1 and then take this derivative with respect to Q. And to get J G2, we need df dg2 respect to Q. Okay, so Q is straightforward. It's T1, theta1, theta2. But in order to find FG1 and FG2, we basically need so I'm going to write I need the position of G1. So position of G1 in frame 0. Okay, that's just basically the forward kinematics, dq. And then jg2 would be dg2 with frame 0, dq. Okay, so all I need is this thing. This is g2. Okay, so we sort of know how to do that. We've already done forward kinematics using homogeneous transformation. That's precisely what I'm going to use. Okay, so let's do it one at a time. Let's get G1 in frame 0. Okay, so here's what we need. G1 in frame 0 is H1 0, and then G1 in frame 1. Actually, I think I use this notation, G1 0, G1 1. Okay, so again the G1, G2, this just means the point, but then the superscript 0 and 1 means the frame. So this is the frame 0, this is the frame 1. So let's write this down. The homogeneous matrix is the one which gives sort of will have cosines, sines, and so on. To find that H1, we need compute the angle made by x1 with respect to x0, right? So I just draw it here. X0 is here, x1 is like this. So just redrawing it over here. So one thing to note is that when we're computing the angle, we always cycle in the counterclockwise direction because counterclockwise is positive. Okay, so we all have to go like this. That's the counterclockwise direction. So the angle made in the counterclockwise direction, note that this is theta 1, is going to be, well, this is 90, this is 90, this is 90. So it's going to be 270 plus theta 1. So you could use 270 plus theta 1, or if you want to go clockwise, like you want to go this way, then you want to use minus of 90 minus theta 1. They'll give you the same answer. So when I write this cosine here, I need the angle between x0 and x1. So I need to put 270 plus theta 1 minus sine 270 plus theta 1. Okay, then sine 270 plus theta 1 cosine 270 plus theta 1. And then this is a placeholder 0, 0. And then here I need to put the position of the origin, or this one, O0. So that's going to be 0, 0, 0, 0, 0, 1. This 1 is again a placeholder in the homogeneous matrix. Next, I want to compute what is the position of G1 in frame 1. So this is this point in frame 1. This is frame 1. So you can see that G1, this point, is along the x1 axis. Okay, so its coordinate is going to have only an x coordinate. So it will be C1 for the x, which is along x1, 0 for the y1 because it's not along the y-axis, y1 axis, and then this 1 is just a placeholder. So that will, if you do this calculation, you will end up with C1 sine theta 1 minus C1 cosine theta 1, and then 1. Okay, and of course that 1 is just a placeholder to make the homogeneous transformation work, but the position is basically this G1 in frame 0, the first two elements. So we've got G1 in frame 0. So we are all set to compute the Jacobian now. The Jacobian, if you go back, is this. Okay, so let me write that down. Jacobian of G1 is dg10 dq. G10 is C1 cosine theta 1. Sorry, C1 sine theta 1, my bad. C1 sine theta 1 minus C1 cosine theta 1. And then Q is theta 1, theta 2. So expanding this out, if you like to think of this as xg1 in frame 0, yg1 in frame 0, those are their functions. So it will be dxg10 with respect to theta 1, dxg1 with respect to 0, d theta 2, and then d yg1 frame 0 d theta 1, dy g1 frame 0 d theta 2. Okay, so it's fairly straightforward to do this. Minus C1. So take the derivative of this thing with respect to theta 1. So sine is, derivative of sine theta 1 is cosine theta 1. Take the derivative of this thing here with respect to theta 2. But you can see there's no theta 2 there, so that'll be 0. Then take the derivative of yg1 with respect to theta 1. So that'll be minus C1 sine theta 1. And then take the derivative of yg1 with respect to theta 2. That's going to be 0. So that's jg1. It's a 2 cross 2 matrix. So velocity of G1 is jg1 q dot. So I'm just going to write the final expression, but you can put the value of q dot, which is theta 1 dot, theta 2 dot. It's going to come out to be c1 cosine theta 1, the 1 dot. An error here. I think I did a mistake here. Hold on. Just so c1 sine theta 1 minus c1. That's correct. Yeah, so this is an error. So I copied it incorrectly. It should be c1 sine theta 1 minus c1. So minus on plus on the first one, negative on the second one. So positive on the first one, negative on the second one. So I should, when I take the derivative, it will be positive here, and then that will be positive. My bad. So it will be, yeah, so positive, and so this answer would come out to be c1. So that's the answer. Okay, so the velocity is clearly a 2 cross 1 matrix, 2 cross 1 vector. Okay. So I wouldn't have the time to go through G2, but I would like you to do G2 yourself. Let me put down the main equations down, and you can try yourself and then get the answer which I'm going to write. So you need to still do VG2. Which is dj dx, sorry, dg2 with respect to 0, dq, q dot. So g2 0 would be h1 0, h2 1, g2 2. So you need to get theta h1 and h1 1 and h1 0. And then once you get that, this will give you the x coordinate, y coordinate of g2. And then you'll have to use this formula. So check this calculation. So when you do that, you will do this, you'll get VG2 is C2 cosine theta 1 plus theta 2 plus L cosine theta 1, C2 sine theta 1 plus theta 2 plus L sine theta 1. So that's the first column, and then C2 cosine theta 1 plus theta 2, C2 sine theta 1 plus theta 2, then theta 1 dot, theta 2 dot. So this is a 2 cross 2 matrix, and this is a 2 cross 1. Clearly, this thing, what you get here, is actually JG2, right? Because JG2 times Q dot. So I've given you answer to JG2. So you might want to get the G2 comma 0, then take the derivative, find that. If you want, you can actually use the symbolic package, which I just showed you.